All right. This is a diagram of, whoa, styrofoam peanut stuff. And so this is the computer-generated styrofoam peanut diagram, the vector flow diagram associated with a system of nonlinear ordinary differential equations that are autonomous. What you might notice about this system is right here, where the cursor's pointing, a bunch of styrofoam peanuts are flowing into that area as if it were a sink. Same thing here. Now in the lower left, there seem to be styrofoam peanuts going away from this region. And then right here, right where the cursor is, some styrofoam peanuts are coming in, but they're being sent to either side and split out. This kind of looks like a saddle. So this isn't anything that we've dealt with, right? Because there are multiple equilibrium solutions and that wasn't happening for us. But we look at this and we're like, man, some of these things look familiar. And then we ask the question, can I get access to these features on this diagram with some mathematics? Because they seem so familiar, maybe I can find some mathematics that'll let me know what's going on with that. So what I would want to tell you about is just a review over the linear mathematics. In the linear mathematics, we had this idea that we could solve x prime is equal to ax. That involved eigenvalues and eigenvectors, but really the pictures that were made, that only depended on the eigenvalues. I mean, it depended on both, really. But if you didn't care, the alignment of your two eigenvectors, you only cared about whether stuff was being drawn in on an eigenvector or being repelled out on an eigenvector. You didn't really need to know the direction of that eigenvector. You just needed to know the exponent, whether it was positive or negative. Also, thinking about our spirals, if you wanted to know whether it spiraled into the origin or out from the origin, you didn't care about clockwise or counterclockwise. You didn't really need to know much. You just needed to know the eigenvalues. Right, so on this left-hand side, which is just a direct copy of a previous slide, what we have is the eigenvalues as they're related to the names of the equilibrium points. Right, and so if pink represents unstable, then what are the other things that we talked about last time that are unstable? A degenerate source was unstable. Anytime you see the word source, that's tantamount to saying unstable. And so the spiral source was also unstable. And then in purple, or no, in red, we had things that were stable. This real sink was stable, and that was by virtue of the exponentials having negative values in their exponent so that when time goes forward, things decay. So that was called a real stable sink. This degenerate sink also has stability. And then when the real part of your complex root is negative, it becomes a sink as well. And that also gives stability to that object. Okay. So on the left-hand side, everything over here, the eigenvalues are tied to a specific phase portrait. And the details of that phase portrait may not be as important as just being able to name and have a visual image in your mind about what phase portrait that is. So if the eigenvalues are so important, then maybe we can find other patterns in the eigenvalues. And so what we want to remember is that if you have this A matrix, which is 2 by 2, there were examples that we did where we wrote the characteristic equation, that quadratic equation, in terms of the matrix trace, which is the upper left plus lower right. I use the letter capital T to represent the matrix trace. Your book in WebAssign will use tau, which is like a T. And then the determinant, which is upper left times lower right minus lower left times upper right. And that's a capital D for determinant. Or your book will use a delta. Okay. But here's the point. If the characteristic equation can be rewritten in terms of traces and determinants, that means your eigenvalues can be rewritten in terms of traces and determinants. So solving that characteristic equation in terms of traces and determinants, I get lambda is equal to trace plus or minus the square root of trace squared minus 4 times determinant over 2. Okay. So eigenvalues lead to pictures. Eigenvalues can be expressed as trace and determinant. That means trace and determinant should be related to the pictures as well. And this is how the relations are made. First, if the determinant is less than 0, then check out this quantity right here. If the determinant is less than 0, then negative 4 times d, well, d is less than 0, so I have t squared minus 4 times a negative number, right? So it's going to be positive plus positive. What this is saying is if the determinant is greater than 0, you're never going to get imaginary numbers. So you're always going to get real roots whenever the determinant of your A matrix is less than 0. Now we can pursue this a bit more, because if I look at this, what's under the square root, t squared minus 4d, well, if determinant is negative, I have t squared minus a negative number. So what that means is that I'm adding a little bit onto t squared. Okay? And so the idea is if I take t squared and I subtract 4 times d, that will be adding a little bit more onto t squared. And then if I take the square root of that number, whatever comes out of that number will be greater than the magnitude of t. So just pretend t is positive for right now. So if you take t squared, add a little bit on, take its square root, whatever number comes out of that, that's going to be bigger than t. So this is what happens. Suppose that t is positive. I'm going to point the cursor at t. T is positive. But then I subtract from t some number that's greater than t. So if I take t and subtract some number that's greater than t, what's going to happen is that will go negative. But if t is positive and I add to it what comes out of this square root, what comes out of this square root right here will be positive as well. So I'll take t and I'll add a positive number to it. That will be positive. And then I'll have t and I'll subtract a number that's bigger than t, and that will go negative. One eigenvalue goes positive, one eigenvalue goes negative, and what we have here is a saddle. The saddles occur whenever the determinant is less than 0. It's just a guarantee. If you go and inspect this, if you go and check those video playlists, there's one from the summer where I give a detailed derivation of these items. But what you need to remember is if determinant is negative, you got a saddle. Guaranteed. Next. Okay, I'm going to move my talking head now so that I can zoom into this section. And what we've determined here is that if you graph trace horizontal axis and you graph determinant vertical axis, whenever you're down in quadrant 3 and 4, those are all pictures associated with eigenvalues. One is positive, one is negative, so you always get a saddle. Okay. Now, if trace is positive and determinant is positive, I'm going to highlight this with maybe a pink. Where am I at when trace and determinant are positive? You are in quadrant 1. Okay. When I'm in quadrant 1, the rule is that I get sources. Why is that? Well, trace and determinant are positive. I'm supposed to get sources. Let's just check it out really quick. If trace is positive, I'm going to put my cursor over by trace being positive, and pretend for a second that this number is 0, t squared minus 4d. You've also chosen a determinant and a trace so that what appears under this radical is 0. So what I'm going to do is I'm just going to erase it. If what's under that radical is 0, it's gone. And if what's under that radical is 0, you're talking about a repeated root. But if you're talking about a repeated root and the trace is positive, this repeated root is positive, and if your eigenvalues are repeated and positive, you have a source. Okay. Now, let's think about it again. Suppose t squared minus 4d goes negative. If t squared minus 4d goes negative, then you're going to get an imaginary number from this square root. So this term right here is the imaginary number. But this term right here with this t, where the cursor is the real part. But if t is positive, that means I have an imaginary number with a positive real part. That means I get a spiral source. And then if I continue the arguing, I'm going to find that all of the sources are relegated to the first quadrant. Okay? I could go back through these arguments, look at what happens when t goes negative, and what I will find is that when t goes negative and the determinant is positive, which puts me in quadrant 2 of the trace determinant plane, I will get sinks. So it turns out that the relationship with traces and determinants to the eigenvalues is really pretty, in that quadrant 3 or 4, that's saddle country. All saddles in the lower half plane. Quadrant 1, when trace is positive and determinant is positive, all sources. Quadrant 2, when trace is negative and determinant is positive, you get sinks. Now there is one special place right in between the two, where trace is 0. If trace is 0, I'm lined up right in between these two quadrants, quadrant 1 and quadrant 2. Right here. And what happens then, we'll check it out. If trace is 0, then this part of the eigenvalue is 0. But if trace is 0, this trace squared underneath the radical is 0. And if determinant is positive, then you're taking the square root of a manifestly negative number, and you're going to get i's. But if you get i's and this term right here is gone, this t is gone, you're not going to get any real part with this I. So it's going to be purely imaginary. And what are you going to get in that region? You're going to get centers. So, trace determinant plane. Lower half plane, when the determinant's negative, saddles. Quadrant 1, when trace is positive, determinant positive, sources. Quadrant 2, when trace is negative, determinant positive, sinks. The break point between quadrant 1 and quadrant 2, the positive determinant axis, centers. So what that means is that, as a summary, I can quickly identify, based on trace and determinant, what your phase portrait's going to look like. I don't know exactly what it's going to look like, but I know roughly what it's going to look like. And if we want to know what type of source or sink, we have to look at t squared minus 4d, right? And that should make some sense, right? If I want to know about what type of source or sink I am once I'm in that quadrant, I've got to figure out what happens under this radical, whether it stays real or goes complex on me. Cool. So I'm going to freeze that. Take any last notes you'd like, and then what I'm going to do is I'm going to move to a bigger picture of the trace determinant plane. Reiterate those statements one more time, but now with pictures. And then move us on to why we might find this useful. So transitioning in 3, 2, 1. That's the big picture of that little diagram that was in the upper right. And now what you have is, this is a saddle, yeah, but here's a computer-generated graph of the peanuts. Everything up here, these are all sinks, a real sink, a repeated sink, a spiral sink, and then a center, and then I didn't include anything for sources, just picture stuff coming out of the origin instead. The reason why I want to highlight this area right up here is that this was all your mass spring stuff. Undamped is a center. Underdamped is a spiral. Critically damped is the repeated route. Over damped is the real sink. Right. So this quadrant, quadrant 2, with this vertical line that separates them, that contains all of your mass spring thought process. Okay. Questions about any of that? For those that are interested in the detailed retelling, go and check out those playlists. There's like a 40-minute dialogue where I demonstrate all of it. I don't know how useful that is for the average person, right? But I did it, and it's there, so you can check it out. What we need to know: determinant less than 0 saddles, quadrant 1 sources, quadrant 2 sinks, brake line in between, centers. Why do we want to know that stuff? Well,